Hello and welcome back. These will be the video notes on operations with cube roots. There is a PDF available if you'd like to print out and follow along. Make sure you have a calculator. Here we're going to talk about how to simplify cube roots and how to rationalize the denominator that contains cube roots. It's this one right here, rationalizing the denominator, that really causes students the biggest problems because it involves cube roots. To simplify a cube root, it's going to be very similar to simplifying regular square roots. Cube root has a cube root symbol in it, which is really similar to a square root, only has a 3 there indicating the third root, not the second root. And in order to be simplified, there cannot be any perfect cube factors other than one inside the radicand, and no fractions are in the radicand, and also no radicals appear in the denominator. That's really similar to the other one. Here are some of the properties. The cube root of a times b is the same thing as the cube root of a times cube root of b, and we can see the example here. We got cube root of 16, which is really cube root of 8, cube root of 2, and 8 happens to be a perfect cube because 2 times 2 times 2, or 2 to the third power, gives you 8. So we can call that 2 cube root of 2. So the cube root of 2 to the third power is really just 2, and that's where this 2 comes from. The same thing with division. The cube root of a over b can be rewritten as the cube root of a over the cube root of b, as long as b doesn't equal 0. Remember, we can't have a 0 in the denominator. So we got the cube root of 5 over the cube root of 27. Well, the cube root of 27 is 3 because 3 to the third power equals 27. Therefore, the cube root of 3 to the third power is 3. And since this equals 27, the cube root of 27 is the same thing as 3. And that's why we go from here to here as a 3. So we're looking for things multiplied by itself 3 times instead of 2 times. That's the difference between cubes and squares or square roots. Example 1, we're going to go ahead and multiply these together. So we end up with the cube root of 6 times 9, which is going to be the cube root of 54. Now what we got to do is look for perfect cubes. Now the best way to do that, because a lot of people don't know what the perfect cubes are, the best way to do that is use a factor tree. So we have our leftovers on this side, we have our prime factors on this side. We take our 54 and go, okay, well I can divide that by 2. I'll put a 2 there. So 54 divided by 2 is going to give me a 27. Well, I can divide that by 3, and that's going to give me a 9. I can divide that by 3, that's going to give me a 3. I can divide that by 3, and that's going to give me a 1, and then I'm done. So when we look for perfect cubes, we are looking for groups of 3. So this right here can be rewritten as 3 to the third power, and this of course is just 2 to the first. So I can rewrite my cube root of 54 as the cube root of 3 to the third times 2 to the first. And since I have a 3, or a multiple of 3 as my exponent, I can break that out as a perfect cube. So cube root of 3 to the third times the cube root of 2. And the cube root of 3 to the third is just going to give me 3 with the cube root of 2 left over. So 3 times the cube root of 2 would be the simplified answer to this problem. Simplifying cube roots again, we have a fraction under the radical, which we're not allowed to do. So we're going to rewrite that as the cube root of n over the cube root of 64. Now before we try to rationalize the denominator, we want to see if we can simplify this cube root. It's easier to simplify cube roots first before you try to rationalize the denominator. It brings the numbers you have to work with down much smaller. Alright, so we're going to go over here and do the same thing. We've got leftover, starts out with 64, and we put our prime factors on this side. So I can divide that by 2, and that's going to give me a 32. And I keep dividing by that same prime number until I can't divide anymore. I got 16 divided by 2, and that gives me 8. Divided by 2, that gives me 4. Divided by 2, that gives me 2. Divided by 2, and that gives me 1, and I'm done. Okay, now some of you probably knew that 64 was a perfect cube to begin with, but what we can see here is we have a group of 3 here, which is 2 to the third, and we have another group of 3, which is 2 to the third. So this is really, on the bottom, I can rewrite this as the cube root of 2 to the third times the cube root of 2 to the third. And the cube root of 2 to the third is 2, and the cube root of 2 to the third is 2, and 2 times 2 is going to come out to just 4. So I can rewrite this as the cube root of n over, and then the cube root of 64, as we said, is going to just simplify to 4, and this ends up becoming our simplified answer. So I didn't have to rationalize the denominator in this example. Okay, here's just a straight up simplify. We have a variable under the radical, and we also have a big number of 280. Well, the 280 is something you are just going to have to go ahead and start dividing out here. So we have leftovers, and we have prime factors here. And as far as the exponent goes, before when we talked about square roots, we said any even number is a perfect square. Well, when we talk about cube roots, we need to find perfect cubes. Where perfect cubes have exponents that are multiples of 3, so into the third, into the sixth, into the ninth, into the 12th. As long as it's a multiple of 3, it's a perfect cube, and it always comes out 1/3 as big as what it started at. So I could rewrite this as the cube root of 280 times, and this 280, I'm going to figure out what that is over here, and into the 8th. What's the next multiple of 8, or sorry, what's the next multiple of 6 below the 8? Well, that would be a cube root of n to the 6th times the remaining cube root of n to the 2nd. So this is a perfect cube because the exponent is a multiple of 3. This one is not, so it will stay underneath. So this will come out as n to the, remember when it's a multiple of 3, we come out as a third of that, so the cube root of that would be n to the 2nd power. And I still have a cube root of n squared. So that's that part of it, but I still got to work on the 280. Now the 280 I'm going to divide by the first prime number that I know will go into that will be a 2, but I'm going to start with a 5 anyway. So 280 divided by 5, and that's going to give me a 56. Now it's an even number, so I can't divide by 5 anymore, so I'm going to divide by 2. Divide by 2, and that's going to give me a 28. No, I can still divide by 2 again. So divide by 2 there, and I get a 14, and divide by 2 again, that brings me to 7, and divide by 7, that brings me to 1, and once I hit 1, I'm done with my factor tree. Now in my list of prime factors, my prime factors are on this side, I'm looking for groups of 3, because every group of 3 is a perfect cube, so that can be rewritten as 2 to the 3rd power. So this portion over here can be written as 2 to the 3rd times 5 times 7. Remember, I still have the 5, and I still have the 7, which don't have any matches of 3's, so I got to leave them as 5 times 7, and they're going to be under the radical themselves. So I have a radical here, and I got a radical here. So cube root of 2 to the 3rd is just going to give me 2, and the cube root of 5 times 7 is going to give me 35. And now I'm just going to multiply these two back together. So the 2 times the n squared is going to give me 2n squared, and the cube root of 35 times the cube root of n squared is just going to give me the cube root of 35n squared. So this is my simplified answer for the original problem. Example 4. In this example, we need to rationalize the denominator. And because there's a cube root in the denominator, this will be a little bit more challenging to figure out than working with rationalizing a denominator that has a square root. First thing you'll have to do, though, is simplify the radical. So I'm going to take my 108 here. Remember, I got leftovers and I got prime factors, my factor tree. And I'm going to divide that by, I'm pretty sure a 3 will go in there. You know, I'm going to start with a 2 because a lot of people don't know why 3 goes in there. So you got to know your multiplication or divisibility rules. So we're going to divide by 2. 108 divided by 2 going to give us 54. And then divide by 2 again, and I have 27. Then I'm going to divide by 3, and 3 is going to give me 9. And then divide by 3, and I'm going to give me 3, and 3 again, and that's going to give me 1, and I'm done. So I have I got 3 3's here, which gives me 3 cubes. So 3 cubes is actually 27, which is a perfect cube. So that's one of them. So I'm going to write the cube root of 3 cubed. And I still have a cube root of, and even though this is not a perfect cube, I'm going to put 2 squared as an exponent, like this, because I'm going to need to know that when I go to rationalize the denominator. Now the n to the 5th power, I'm going to break that out into n to the third power because that's a perfect cube, and what's left over is going to be n to the second power. So n to the third times n to the second will give me the n to the fifth. Well, the perfect cubes are here and here. The ones that are not perfect cubed are this one and this one, and I forgot a perfect cube symbol here. There we go. So the first one's going to be, I'm going to bring down my 5. The cube root of 3 to the third is just 3. And the cube root of n to the third is just n. And these two need to be multiplied back together because they are not perfect cubes. But when I go to multiply them together, I am not going to do 2 times 2 and call it 4. I'm going to leave it as 2 to the second power and n to the second power. So I haven't rationalized the denominator, but I have simplified the radical in the denominator. Now here's where we rationalize the denominator. I do have to multiply by something that makes a perfect cube. So I'm going to multiply by the cube root of something. And the trick is figuring out what that something is. Well, we look at our first number here, and you see it's 2 to the second. In order to make it a perfect cube, it needs to be 2 to the third. So what I need to do is multiply by 2 to the first. And the same thing here. In order to make an n to the third power, I already have an n to the second, I have to multiply it by n to the first. So I'm going to multiply by the cube root of 2 to the first and n to the first. And when I do that, the top will just be 5 cube root of 2n. And the bottom is going to be 3n times. Now when I multiply these together, I will have a 2 to the third power times n to the third power. And when I take the cube root of both, I'll end up with just a 2 times n. So I'll end up with a cube root of 2 to the third power, n to the third power when I multiply them together. And the cube root of them is just 2n. Now I have a 3n times 2n in the denominator, which is going to give me a 6n in the denominator. And I have a 5 cube root of 2n. That is my simplified answer. The trick is figuring out what do you have to multiply over here, because you can't just multiply it by itself like you can with square roots to cancel them out. You have to figure out what the exponent needs to be. In this case, it needed to be a power of 1 for both of those. Example 5, this is just another distribution problem. So we're going to go ahead and distribute. I'm going to multiply here, and that's going to give us a cube root of 8. Then I'll worry about simplifying afterwards. Then we're going to distribute here, and that's going to give us a negative cube root of 4. Then we're going to multiply here, and that's going to give us a positive 2 cube root of 2. And we're going to multiply here, and that's going to give us a negative 2. All right, now this and this are not perfect cubes. 4 only breaks down into 2 times 2, and 2, of course, is 2 to the first power. So I'm not going to have an exponent of 3, so I don't have any perfect cubes there. However, 8 can be broken down into 2 to the third power. So that is a perfect cube. Well, the cube root of 8, or the cube root of 2 cubed, is just 2. Bring down the rest of the problem. 3 and 4, cube root of 4, plus 2. We got the cube root of 2 and minus 2. This and this are like terms, so 2 minus 2 is going to give you a 0, so they basically just drop out of the problem. However, these two are not like terms. They have to have the same number under the radical sign, and they don't have them there. So the cube root of 4 and the cube root of 2 are not considered like terms. So the best way to express this is just to call it the negative cube root of 4 plus 2 cube root of 2. And this becomes your final simplified answer.